With the Monday review, if you can't be here for whatever reason, I understand it. I know that we've kind of boxed you in a little bit by changing the schedule on you. We're going to do it this way, then we're going to do it that way, we're going to do it another way. But if you can be here, I'd encourage you to. You're going to get a lot more out of it face-to-face in person than online. Any questions? All right, so let's move then into talking about what we were looking at after Monday's virtual session. And so in Monday's virtual session, you did an activity that went through the primary types of intermolecular forces: dispersion forces, hydrogen bonding, and dipole-dipole forces. These forces all have factors that impact on them. Now, what I want to talk about before we move on is that dispersion forces have the most variability within them, because since they do not have a permanent dipole, the temporary dipole that forms can vary in strength and can vary in capability of forming that dipole. We call that something called polarizability. How likely is it to become polarized, to have that temporary positive and negative? And there are two real factors that go into that dispersion. You saw it in last week's lab. The first, atomic size. Now, atomic size, we tend to estimate using molar mass. And it comes from the idea that if you have a larger atom or a larger molecule, it's more polarizable. The reason why? There are more electrons. When you have more electrons, the opportunity to have a greater polarity becomes, well, greater, because you need fewer imbalances to make it happen. The best way to think about that is with an illustration. I'm going to go back to the whiteboard here for just a second. Let's just say, for the sake of argument, that I've got two different atoms. In this atom, I have 4 electrons. In this one, I have 10. When it comes to polarizability, there are only a few combinations in this group of 4 that would actually create a polar dipole. I could have 3 on this side and 1 on this side. I could have 3 on this side and 1 on this side, or I could have all 4 on either side. In total, there would be 4 different polar combinations. But with 10, there are really only a couple of combinations that are nonpolar, and many more that are at least slightly polar. I could have 6 on one side and 4 on the other side. I could obviously flip those around. I could have 7 on one side and 3 on the other. I could flip that around. 8 on one side, 2 on the other. I could flip that around. 9 on one side, 1 on the other. Also the reverse. 10 on one side, and so 10, 9, 8, 7, 6 times 2, 10 different polar combinations. And so this is the trend that we're working off of. The more electrons we add, the easier it is to polarize the molecule, because all it takes is a little bit of imbalance on one side or the other. So when I had 10 electrons, I just had to go away from 5 on each side. Turn one of those over, and it becomes polarized, even slightly polarized. That would still garner some attraction. If I went from 10 electrons to 20, I'd get even more combinations. If I went from 20 electrons to 50, I'd get even more combinations. So this concept, again, relating itself to molar mass, because molar mass can ultimately give us an idea of electron count. The heavier something is, the more protons and electrons it's going to have. And in particular, we're looking at the electrons that are mattering here. The other impact is shape of molecules. With shape, we're looking at changes in surface area. And the ones that have more surface area, the more interaction those molecules can have, the more that they can touch each other, the more attraction they're going to have to each other. You saw this in particular when we compared the hexane and the cyclohexane in that vapor pressure lab last week. Generally speaking, linear molecules tend to have higher levels of dispersion, meaning those layers, those linear chains can just kind of sit on top of each other and interact far greater than things that are more branched out. Now rings tend to actually have even greater interaction because they can stack on top of each other. And so what most of you hopefully saw is that your cyclohexane had a considerably lower vapor pressure than your other molecules. Why? Because those rings are able to stack on top of each other like poker chips. And because of that increased interaction, you're going to see a lot greater level of attraction. So if we look at size, here we are comparing size versus boiling point, and we can see that as our noble gases get larger, so do our boiling points as a result. And this is true not only for atomic gases, but also molecular gases as well. The bigger the molar mass, the greater the boiling point. To the point where we can actually see bromine at a boiling point of 332 Kelvin is actually a liquid at room temperature. Iodine at 457 Kelvin is actually a solid at room temperature, as is astatine. Their intermolecular forces are so great that they actually take on a more condensed phase, a solid, than a liquid. We can see this in hydrocarbon chains as well. starting with methane right here, a single carbon chain, going all the way up to octane here, a 8-carbon chain. And we can see that the relationship here isn't linear, it's curvilinear. But there's a definitive positive trend as our molecular size increases. We can also see in the form of shape, what we have are something called constitutional isomers. These are things that have the same chemical formula, but their arrangement in three-dimensional space and shape is different because of different kinds of bonding that exist. And again, the trend here, those that have higher surface area have stronger interactions, and therefore lower boiling points. So the more linear the shape is, the less branched out it is, the more surface area it has, the greater the attractions will be. And so we can see this in these constitutional isomers here. All three of these compounds have the formula C5H12. They're all derivatives of pentane. In pentane, we have a boiling point of 309 Kelvin. If I take one of those end groups and move it to form a second bond with that carbon here, what I would have is 2-methylbutane. And we see that in 2-methylbutane, we see a drop in boiling point. Went down by about 8 degrees. Why? This little branch group right here is a little bit more bulky. Other methylbutanes have a little bit more trouble interacting, especially with that center carbon that's now surrounded by 3 other carbons. And as a result, we get a decrease in interaction. And that decrease manifests itself again when we see the same thing happen on the other side. And now we've got this, what we call a quaternary carbon, a carbon bonded to 4 other carbons. And our boiling point drops by nearly 20 degrees in that case. And again, the reason why this carbon in the middle is now pretty much completely inaccessible. The only points of contact are just on those end groups, whereas we had pretty much contact all over the original pentane and over most of the methylbutane. So shape does make a considerable difference. The bulkier the shape is, the less access that certain atoms have to the outside world, the less interaction they're going to have. So let's start to apply these to our discussions of physical properties. And what we need to know, intermolecular forces will dictate physical properties based upon the strength of the interactions of the molecules with each other. The stronger the intermolecular forces are, the harder those forces will be to overcome. Now, one thing that we do need to understand is that London dispersion forces are not exclusive to nonpolar molecules. We kind of talked about them on Monday as being separate things. But we have to understand that intermolecular forces, especially dispersion forces, because they are associated with the random movement of electrons, we find them in anything that has electrons. Now, we don't really talk about them in polar molecules because the dipole dipole forces that exist in polar molecules are so much stronger than dispersion forces that they kind of just mute them out. However, we do find that dispersion forces have an impact when we start comparing molecules that have similar types of dipole forces to help us to differentiate the two. So if I'm looking at methanol versus ethanol, CH3OH versus C2H5OH, both of these exhibit hydrogen bonding. Both of these exhibit dipole-dipole forces. You would look at both of them and say, okay, they're both going to have pretty considerably high boiling points. How do I know that ethanol has a higher boiling point than methanol? Well, the dispersion forces are going to be greater in the ethanol than in the methanol, because ethanol is a heavier molecule. And that's where dispersion forces make the biggest impact on polar substances, is when we're comparing one polar substance versus another. So if I have two molecules that have the same kind of characteristic force at play, I can use London dispersion forces to help me differentiate between them. The stronger the intermolecular forces are, the more difficult they are to overcome. What this tends to mean is this indicates a tendency to stay solid or liquid, especially liquid. So we're going to look at 4 different physical properties, 2 of which are related to each other very, very intimately. And we're going to compare the intermolecular forces to each other to help us determine and rank, okay, this substance is going to have the highest boiling point. This substance is going to have the lowest vapor pressure. This substance is going to have the greatest viscosity. And this is a big part of what your skill builder in lab this week is all about, is identifying intermolecular forces, ranking them, and applying them to physical properties. So if you haven't looked at that skill builder yet, you're going to see these skills come up there very, very prominently. Let's look at viscosity first. By definition, viscosity is the measure of resistance of flow for a liquid. The more difficult a liquid is to pour or move, the greater its viscosity tends to be. Now, the primary factor that impacts viscosity are your intermolecular forces. What we tend to see is that stronger intermolecular forces tend to lead to greater viscosity. And so if I compare, say, water versus maple syrup, which one of those would have a greater viscosity? Syrup. Syrup's stickier, it is harder to flow. You put it in the refrigerator, sometimes it can just brick up on you. Why is the viscosity of maple syrup greater than that of plain water? Ben? Okay, where do those intermolecular forces come from? What is in the syrup that has a greater intermolecular force than water to itself? Sugar. Yeah, you've got sucrose molecules in there. Sucrose molecules are polar molecules that hydrogen bond but have 12 carbons in them. So yeah, there's a little bit of water in maple syrup. There's a heck of a lot of sugar. And so those sugar molecules sticking together make it viscous. Very similar to what we see in honey. Why is honey crystallized often on us? Well, because some of the water kind of leaks out. You end up with all that sugar left over, and the sugar crystals kind of crystallize inside of the honey jar. Now, in the event that you brick up your maple syrup in the refrigerator, what do you do to make it so that you can pour it on your pancakes? You heat it up. You put it in the microwave, or you put it in a hot water bath. You do something to warm it up. Why does that work? Well, that's the second factor. Temperature tends to decrease viscosity. So at higher temperatures, you have a lower viscosity. It's one of the reasons why you go to a restaurant and you order pancakes, they usually serve you warm maple syrup so that it's easy to pour. So those are the two factors. Temperature obviously has an impact. What we're most interested in is the intermolecular force, though. And so we can see this. Now, viscosity is measured in a unit called centipoise. You don't need to know that, but that's what the CP stands for. And what we can see is that our general trend, these are all organic, all nonpolar. And so all that we're looking at are dispersion forces. And we see that as our molar mass increases, so does our viscosity, which makes sense. I increase my London dispersion force. I increase my viscosity. Same thing would be true with polar molecules and each other as well. Going back to our maple syrup example, we have hydrogen bonding in water. We have hydrogen bonding in the sucrose in syrup. What's the big difference between them? Water has a molar mass of 18. Sucrose has a molar mass of 300, something like that. Big difference in mass. Big difference in London forces between them. And as a result, greater viscosity in the syrup. For vapor pressure and boiling point, we present these two together because they are very closely related. Now, as you saw in last week's lab, vapor pressure is the measurement of how much a liquid is evaporating at a given temperature. So I set out a liquid, I let it evaporate, just as it does naturally. If I close the container and trap that vapor will start to exert a pressure on the surroundings. That is the vapor pressure of the liquid. And so in that particular scenario, the vapor pressure is related to how much liquid has evaporated. The more the liquid evaporates, the more vapor pressure we're going to get. But here's something we haven't talked about yet, and it's an important thing to note. When a substance's vapor pressure equals the atmospheric pressure, the temperature at which that happens, we refer to collectively as the boiling point of the liquid. So evaporation, vaporization, is a process that occurs continuously at all temperatures. Now, some temperatures are more prone to it than others, but it happens at all temperatures. You set out a jar of water right now, I guarantee you some of it will have evaporated by the end of the hour. That's not the same thing as boiling, though. In order to get boiling, I need to have the vapor pressure match the atmospheric pressure, and whatever that temperature is, that's the boiling point. So when we say that the boiling point of water is 100 degrees Celsius, well, that implies that we are at sea level. And that also tells you that the vapor pressure and the atmospheric pressure have met each other. And it's for this reason why we can exhibit different boiling points at different elevations. You know, why do certain kinds of baked goods have high altitude directions on them? Well, because the air is thinner in the mountains, which means the atmospheric pressure is lower, which means water is going to boil at a lower temperature. Water boiling at a lower temperature, well, that's as high as the temperature can go internally until all the water dissipates, which means that the food is going to cook at a lower temperature, which means it's probably going to take longer to cook. That's why those high altitude directions always, you know, seem to add 10 or 15 minutes to whatever recipe that you're doing. Now, our relationship between intermolecular forces and vapor pressure and boiling point are all the same. So let's think about what this relationship is. Give me some ideas. All right, Ben, you got something? Well, yes and no, but we're talking specifically about intermolecular forces here, not temperature. All right, Jaron?
Vapor pressure. The intermolecular force room temperature, higher vapor pressure, it'll have a lower boiling. Once you add heat to it, it'll be easier for it to separate.
Okay, one thing we can pull out of that, vapor pressure and boiling point are inversely related. If something has a high vapor pressure, it's going to have a low boiling point. If it has a low vapor pressure, it's going to have a high boiling point. Those things are true. Now, what specifically is the relationship between intermolecular force and vapor pressure then?
The weaker the intermolecular force, the higher the pressure.
Okay. That's true as well. Intermolecular forces and vapor pressure are also inversely related, which sets us up with a weird double negative. Intermolecular forces are inversely related to vapor pressure, which is inversely related to boiling point. Well, two negatives in this case make a positive, which means that the third statement we could say is that intermolecular forces and boiling point are directly related. So all three of these concepts are related to each other. They're just related in different ways. When I have strong intermolecular forces, I'm going to have low vapor pressure and high boiling point. When I have weak intermolecular forces, I'm going to have high vapor pressure and low boiling point. All three are interrelated. So with that in mind, let's look at another example here. In this graph, I have the boiling points of all of the hydrides for pretty much group 14 to 17. So this part of the periodic table that possesses most of our non-metals, this graph represents all of them. So drawing a diagonal from carbon to iodine and boxing it in around there. If I look at the methane, the carbon group, I see the trend that I would expect. None of these are polar bonds. They all tend to follow a relatively upward path. And that is what we expect. Intermolecular forces, they're all nonpolar, so we're just looking at London forces. And we know that as London forces increase, intermolecular forces increase, which means boiling point's going to increase. So the trend here is for 14 is pretty good. And we see that other than in this spot right here, the group 15, 16, and 17s all follow similar suit, where we've got an increase in London dispersion forces driving these increases in boiling point temperature. But what gives? Why are these 3 points, the water, hydrogen fluoride, and ammonia, why are they out of place? Why don't they follow the same trend? Well, all of the ones in group 15, 16, 17 are polar. What's special about those 3? What do they have that the other polar molecules in their groups do not?
They start off with high boiling points.
Okay, they do have high boiling points. The question is, why do they have the high boiling points? There's that third type of intermolecular force. There's London dispersion, dipole-dipole, and hydrogen bonding. These 3 that are so out of place are so out of place because they exhibit hydrogen bonding. Remember, hydrogen bonding exists in polar molecules that contain either NH, OH, or FH bonds. And so the reason these stand out head and shoulders above the rest is they're not just polar, they're polar plus hydrogen bonding. And that extra boost of polarity coming from a combination of the size of the molecules, the fact that that electronegativity is so compacted, plus their additional polarity, makes them a lot more polarizable, a lot more strong in their attraction than others. And so they outperform pretty much everything else in the group because of that level of attraction. So let's start to summarize this. We know that the stronger the intermolecular forces are, the lower the vapor pressure is going to be. Primary reason, intermolecular forces are keeping the molecules close together. The stronger the forces are, the more compacted those molecules are going to be to each other, the more difficult it's going to be to vaporize them. Because remember, for vaporization, I have to literally take a liquid sample that is full of all of these molecules, and provide it with enough energy to take one of those molecules and turn it into a gas. The more strongly attracted these molecules are, the more difficult it's going to be to get them to vaporize. The less attracted they are to each other, the easier it is, the less energy it's going to take to rip them apart from each other. And now we can see why there's a temperature impact on vapor pressure as well. Why does vapor pressure increase with temperature? Well, the increase in temperature provides that increase of energy. Now we're putting more energy into the liquid, and that's providing more energy for the molecules to actually break apart from each other. Which is why eventually all liquids will boil. All right, our last trend concerns solubility. Now, with solubility, we do have to introduce a couple of new terms. We have our solvent. Solvent, by definition, is the component of the solution that is present in the largest amount. We tend to use moles to describe that largest amount. Solute, on the other hand, would represent any other component of the solution that is not the solvent. Now, most commonly, we are dealing with solutions that are water-based, aqueous solutions. And so water would be the solvent in those cases, and whatever is dissolved in the water would be the solute or solutes. We measure solubility of a solute based upon how much of that substance can dissolve in a given amount of solution. And we usually measure that in terms of grams of solute per 100 grams of solvent. That is what our unit for solubility usually is. So if I tell you the solubility limit of sodium chloride in water, I would give you a mass of sodium chloride per 100 grams of water. That way we're always kind of going from a standardized value. Now, what can we say about solubility? Well, there's another term that we need to throw in here. Miscible or miscibility. Substances that are miscible are liquid in nature and can dissolve in each other in any proportion. Alcohol and water is a terrific example of miscibility. Go down the liquor cabinet or down the liquor aisle of Walmart, you're going to see lots of different concentrations of alcohol and water. They go by fancy names like proof, but proofing is just a concentration value that's been doubled. You can get anything from practically water with just a tiny bit of alcohol mixed in to practically pure alcohol with just a tiny bit of water mixed in. That's the definition of miscibility. The two are soluble in each other in pretty much any proportion that you can think of. Substances that are not miscible are ones that will not dissolve in each other really in any proportion. We think of things like oil and water, gasoline and water. Doesn't matter what we do, they won't dissolve in each other. When it comes to whether something will dissolve or won't dissolve, it has to do with the interactions of the intermolecular forces between the molecules in question. The generic trend that we like to use here, like dissolves like. Substances with similar kinds of intermolecular forces, polar and polar, they tend to dissolve in each other. Nonpolar and nonpolar, they tend to dissolve in each other. Polar and nonpolar, they don't tend to dissolve in each other very well at all. The only times when we really even see anything like that are with an induced dipole, where the presence of a dipole causes a nonpolar molecule to bend slightly, creating a temporary dipole situation. This is what happens in oxygen. So oxygen is a linear molecule. Water actually causes it to slightly bend in its structure. And in that little bit of bending, we create a slightly positive area and a slightly negative area. And that allows oxygen to dissolve slightly in water, which is a good thing because that means that we have dissolved oxygen in water, and that allows things like fish to breathe and other things to live underwater. When we have substances that have both polar and nonpolar centers, they often will compete with each other in terms of what kind of solvent it fits best in. Generally speaking, nonpolar molecules are described as hydrophobic. Literal translation of hydrophobic means water-fearing. They're going to run away from water. And that's exactly what happens when we take something like oil and put it into water. The oil literally skitters away from it and separates itself from the water that we just added. Things that have polar groups tend to be hydrophilic. Literal translation there, water-loving. And again, this speaks to our idea of like dissolves like. Now, if we have a situation, let's say that we have an alcohol that has a very long hydrocarbon chain, like octanol. What we find is that as the nonpolar character increases on those kinds of molecules, they become less and less soluble in water. So octanol is barely soluble in water. Hexanol, which only has 6 carbons, is slightly more soluble in water. Butanol is even more soluble in water. Ethanol, with only 2 carbons, pretty darn polar, it's completely miscible in water. And so when we see these kinds of competing things happening, we have to evaluate the polar versus the nonpolar character, and that's going to tell us where it's going to dissolve and how it's going to dissolve. And that's where we're going to stop for today. So on Friday, we will talk about the last part of chapter 6 concerning phase diagrams. That'll be the subject of Friday night's post-lecture as well. And we'll probably dive just a little bit into chapter 7, get that thing started as well. Have a good afternoon.